Yes, good.
Yeah, so welcome everybody, and we welcome the first speaker, Eugenia Franco from Bonn University, who will tell us about property of adaptation in systems out of equilibrium. Please.
Okay, thank you very much for the invitation and for the organization of this seminar. So the work that I want to present today has been done in collaboration with Juan Velázquez from the University of Bonn. And the focus of my talk will be the property of adaptation. So, I don't know why there is no title. So one very important property of a biochemical system is the property of detail balance. So a chemical network is at detail balance if every reaction is balanced by its reverse reaction at equilibrium. So later I will give more details and I will present this definition in detail. But the idea is that when a system satisfies the detail balance condition, each reaction is balanced by its reverse reaction. And this property is particularly relevant in biological applications. And the reason is that many biological systems operate in out of equilibrium conditions. And the reason is that they must spend energy in order to work. For instance, they must use a molecule of ATP in order to complete one reaction or several reactions. And this, from the mathematical point of view, has the consequence that the equations that are used to model this system do not satisfy the detail balance property. So the goal of this talk is to understand what is the relation between the detail balance property, or better, the lack of detail balance, and the property of adaptation. Adaptation is a property that is common in many biological systems. And it means essentially that the system reacts to changes in a signal, to gradients of a signal, instead of absolute value of the signal. So I will provide more details later. But this property of adaptation is really typical of a biological system. And therefore, what we are asking in this talk is whether this property of adaptation requires the system to be out of equilibrium in order to hold. This is the motivation for the talk. So the plan, I will briefly introduce what I mean with the chemical system, and in particular with the conservative chemical system. And then I will state in detail the definition of detail balance and what are its consequences. Then I will go to the property of adaptation, and I will study what is the relation with the property of detail balance. So, a chemical reaction network, this I think is
Sorry, now we
known, but...
sorry, the slide, because there is this on the title. Yeah, somehow, I don't know where. Yes, I don't know how to, you can put. Yeah, perfect. But then you have to mute yourself because you mute. Right.
Sorry.
Sorry.
Okay, so I think this is known, but I want to fix the notation that I'm using. So here a chemical reaction network is a set of substances, omega, that is a finite set. And these substances interact via a set of chemical reactions that for us here are a vector with entries that are integer. And each of these reactions take place at some given rates that I'm denoting with the K of R. So the reaction R, here calligraphic R is the set of the reactions, transforms a set of reactants in a set of products. And here, in this notation, the negative entries of the vector of reaction correspond to the set of the reactants, so the initial substances of the reaction that I'm calling IR in the slide. And the positive entry corresponds to the set of products. So the set of final substances of the reaction. And in all this talk, I'm going to assume that mass action hold, and I will always consider networks that are bidirectional. So each reaction has a reverse reaction. And the reason is that I'm interested in the property of detail balance. So we need, in order to have detail balance, we need to have one reaction and also its reverse. And then one can simply write the usual system of ODEs that describe the evolution in time of the vector of the concentration of substances in the chemical network. This is just this equation. JR here is the flux of chemicals due to the reaction R and its reverse reaction. So on one side, here we have the rate of the reaction R times the product of the concentration of the reactants. And here we have the same, but for the reverse reaction. So this is the flux due to the reaction R. And an important property that we want to study for chemical reaction network is whether or not the network is conservative. And in particular, we can define a set of conservation laws. This set is the orthogonal of the span of all the reactions. So every conservation law is orthogonal to all the reactions that we have in the network. And this implies that a conservation law in this set does exactly what we expect. So this means that the scalar product of this vector M of the conservation law times the vector of the concentration is constant in time. And we say that the network is conservative if there exists a conservation law that is strictly positive. So it means that all the entry must be strictly positive. So we cannot have zeros in these vectors. And the reason why this is the definition of conservative network is that this means that every substance appears in at least one conservation law. So in some sense, every substance is conserved in the system. Okay. Then I want to provide the precise definition of detail balance. As I said before, detail balance means that each reaction is balanced by its reverse reaction at the steady state. In particular, this means that there exists a vector, n, a positive vector, that is such that this equality holds, equality 1. So here, this essentially means that for every reaction R, the flux that I introduced before, this flux JR, is equal to 0 for this vector n. In particular, this vector n is a steady state of the system. Okay, so when detail balance holds, we also know that all the steady state satisfy equality 1. And in particular, this implies that when we have two different steady states, N1 and N2, they in some sense differ for a conservation law. More precisely, the logarithm of the quotient between the two steady states must be a conserved quantity, must be in this space M. Why are we interested from the mathematical point of view? Why is detail balance an important property? So essentially it gives for free the existence of a natural approved functional, because it gives for free the existence of a non-increasing free energy, and therefore this is a tool to prove the existence of a globally stable steady state for the system of ODEs. When detail balance, when we have a lack of detail balance, we can have much richer behavior. So, for instance, we can have periodic solution, oscillations, and the dynamics is richer in the cases in which detail balance is lacking. So, in the previous slide, I mentioned.
Can I ask you a question on
yes.
the previous? But so basically, on the previous slide, so you say
yes.
Because it seems that a chemical reaction network satisfies the detail balance property, but so you consider for this consequence to be at that steady state for which this property holds. I mean, in the sense that as is written, it looks that it could also, it's a property of a reaction network, of a topology of the reaction network, because you said there exists,
Yes.
but the consequences are only at this, so a bit confusing in that sense.
So there exists a vector
Yes.
such that this equality holds for every reaction. So it's a global property of the network, because this equality must be satisfied at each reaction. There is also what is called the circuit condition, that is a condition on the cycles of the network. So essentially, if you don't have cycles in the network, then detail balance holds. So this property is connected also with the topology of the network. Yes. I don't know if the question. Yes.
When you have bidirectional, you can so how you cannot have this for a bidirectional if you put the rates. If you put all the rates,
you can have a steady state for which these fluxes are not all equal to 0. This is something you can have.
Yeah, but if you have bidirectional, you can always make there is always exists. That's why I'm a bit confused.
So bidirectional, I just means that for every reaction there exists the reverse reaction belongs to the system, but this does not mean that this equality holds. I don't. Yes.
But if you put all n equal 1 and all k's equal 1, then you have this. So you always exist. That's what.
So if you put all n equal to 1, you must have kr equal to k minus r.
Yeah, like all r equal to 1, all k is equal to 1.
Mm-hmm.
And then you always have, if it's bidirectional, you always have there exists 1. But I think that my question is basically that you study the point where you have. So the
no. This is not true that it always exists one vector that satisfies this equality.
Right. No, Nicola.
No,
it's not only in the condition
on the rates. It's a condition on the rates.
Yes,
so it depends on the rates and on the topology of the reactions taking place. So I don't have here, in this slide, I don't think I have a concrete example in which you break this property of detail balance, but yeah, there are
maybe
examples.
I don't want to disrupt so much, sorry.
Yes, but maybe later I can show you.
I didn't understand something basic, so so which is all fine, so fine, please continue.
No, but later I can show you an example in which this condition is broken, yes. Okay, then I go on. Okay, so here what I want to explain is I would like to explain why detail balance, why is typical to have lack of detail balance in biochemical systems. So in principle, this detail balance property is a property that follows from a physical principle of microscopic reversibility. And every chemical reaction should satisfy in principle the detail balance property if the system does not exchange substances with the environment. However, many biochemical systems do not satisfy this property. And the motivation for that is that these systems exchange chemicals with the environment. And they can be described by effective systems that don't explicitly exchange matter with the environment, but do not satisfy detail balance. So in order to explain this, it's better if I present an example. So in this example, I have a reaction in which you have that the substance A combined with a molecule of ATP produces the substance B plus a molecule of ADP. And we will also assume we have also the reverse reaction. And in principle, what we have is that the detail balance property holds. So we have this condition is satisfied. And now we can assume that since this reaction take place in an environment, we can assume that due to the exchange of molecules of ATP and ADP with the environment, we can have that the concentration of ATP and ADP is fixed at certain concentrations that might differ from the steady state. And this has the consequence that we can write an effective system that transforms the substance A in the substance B and vice versa, that do not explicitly depend on the ATP substances or ATP and ADP. The fact that an ATP molecule and an ADP molecule is consumed or produced is hidden in the chemical rates. And this effective system has a different steady state compared to the one that we had before. And in particular, in principle, detailed balance might fail. It fails unless the concentration of ATP and ADP is selected at very specific concentrations. So in general, detailed balance fails. So this was just to motivate why I'm saying that detailed balance fails in many biochemical systems. We have more details in this about this reduction in this paper, in which we provide some topological conditions that guarantee either that detailed balance is broken when we reduce a system by freezing some concentrations, or that detailed balance is going to be broken in the reduction. And we also prove that every chemical system that does not satisfy detailed balance can be completed with a larger systems that satisfy detailed balance. And this larger system involved more substances. So I don't have time to go into the details of this, but here is a reference. Okay, and now to be able to speak about the property of adaptation, I need to before explain what it is a signaling system. So this is just a chemical network in which one substance is exchanged, which is the signal, is exchanged with the environment. So here in this system of ODEs that I'm writing, without the red part, is just the system of ODEs that describe the evolution in time of a chemical reaction network. But here we assume that we have fluxes of signal, substance 1, with the environment. And so this red term here accounts for that. And in particular, we assume that this external flux is such that the concentration of the substance 1 is just given by a function f that is given. Okay, and here I will say that a signaling system is conservative if the underlying chemical reaction networks, so in which we do not exchange the substance 1 with the environment, is conservative. And then we say that a signaling system satisfies the detailed balance condition, the detailed balance property, again, if the underlying system chemical reaction networks satisfy detailed balance. Okay. And what is the property of adaptation for this type of system? So we take a signaling system and we assume that at time t equal to 0 is at the equilibrium, so is at the steady state. And then in order to have that the adaptation property holds for this signaling system, we need 3 assumptions to be satisfied. So first of all, we need to have, the adaptation property is always with respect to a substance P that is different from the signal. This substance P, I call it product. So the first assumption that must be satisfied is that the vector of the concentration must converge to a steady state. This is essentially to simplify a bit the situation, the problem. The second assumption that must be satisfied is that the system responds to changes in the signal. More precisely, we want to see a change in the concentration of the products after a change in the concentration of the signal. And the third property is the following. We need to assume that after a transient time, the concentration of the product returns to the level that it had before the signal started. So I can maybe re-explain using this figure. F here is the signal, and P is the concentration of product. We start from when the system time equal to 0 is at a steady state. And then what we make the signal change. The signal concentration in this case increases. And what we need to see is, at the beginning, we need to see that the concentration of product changes. But after a large enough time, so here time t tends to infinity, the concentration of product converges to the value that it had before the signal, even if the concentration of signal changed. So this is the main idea. This property of adaptation is typical of many signaling systems. An example is, for instance, chemotaxis. And here the question is this property of adaptation possible in systems that satisfy detail balance? And the answer here is yes. So we need the following assumptions. So we assume the signal converges to a steady state at time tends to infinity. We assume the signaling system satisfies this property of detail balance, and that the network is connected. But we assume that the system is not conservative. So the substance P is exchanged with the environment. And this in particular implies that for every conservation law, the P entry is equal to 0. And then if these assumptions are satisfied, what we can prove is that unless the parameters are fine-tuned, the property of adaptation holds. I just give an idea of the proof. So assumption 1 and 2 are needed in order to guarantee that the system converges to a steady state as time tends to infinity. The connectivity of the network is needed in order to guarantee that when we change the signal, the concentration of the substance P changes. We need the product to be connected to the signal in order to hope that there is a reaction in the product after changes in the signal. And then we need we use the detail balance property to have that the initial state of the system, n0, differs from the final state, which is the steady state, essentially by a conservation law. And due to the shape of the conservation laws, in particular due to the fact that the system exchanges the product with the environment, we have that the concentration of product at the steady state is actually equal to the concentration of product that we had at the initial state. So the product returns to the level that it had before the signal. But a crucial assumption here is that the system is not conservative. And indeed, what we can prove is that if a signaling system satisfies the detail balance property, plus is conservative, and is conservative, then this property of adaptation does not hold unless the reaction rates are fine-tuned or the conservation laws, conserved quantities, satisfy a very specific factorization assumption. So essentially here I'm saying that stable adaptation is impossible in signaling systems with detail balance that are conservative, unless a very specific assumption on the conserved quantity holds. This factorization assumption is a bit technical, but I will present it via an example. So here I have this chemical reaction network, and here we have two conservation laws. One is the blue and the one is the pink. And what we have is that the blue conservation law involves only the substance 1 and 2. And the conservation law, which is pink, involves only the constant 3 and 4. So in some sense, this conservation law factorizes the space, the set of the substances, produce a partition in the set of the substances. We do not have substances that appear in both the conservation laws. And when this situation holds, we can assume, for instance, detail balance. And we already know that this system is conservative because each substance appears in at least one conservation law. This altogether implies that the concentration of the substance 4 and also of the substance 3 is totally independent on the substance 1, also on the substance 2. So if we take, for instance, 1 as a signal and 4 as a product, we do have the adaptation property, even if the system satisfies little balance and is conservative. So this is what this factorization assumption wants to means, and yeah, we need to exclude this from our theorem, these situations from our theorem. I also want to stress one thing, that there is a classic, probably the most classical model of adaptation is a network, a signaling system that satisfies little balance and that is conservative. So I want to explain that there is no contradiction between our results and this classical model. So in this model, the substances are ligand, L, and then we have two different types of receptors, R and D, and then two different types of complexes, X and Y. And the reactions that take place are attachment of a ligand to the two types of receptors, and then the type of receptor and type of complex can interchange. So we have the receptor of type R can become receptor of type D with a certain rate and vice versa. Here we have certain natural conservation laws. The number of ligands is conserved and the number of receptors is conserved. And in particular, the network is conservative. And in the paper, it is assumed that the chemical rates are such that the detail balance property holds. And this in particular implies that and they can prove in this paper that the property of adaptation holds. However, they prove it only for fine-tuned parameters. So adaptation in this case is not stable. So there is no contradiction with our results. So I think I finished here. Maybe I can mention something. In this work, we always consider mass action. Other kinetics usually can be obtained as limits of chemical networks with mass action. But in any case, in this talk, I focused only on mass action systems. Okay, thank you.
Yes, thank you very much. So typically we say